In today's lesson, we are going to be looking at equations and roots. So this is just going to be a continuation of our factoring. It's going to kind of apply it to our quadratics now and kind of give us the reason of why we want to be able to factor. So just as a warm-up, we want to factor the following. So x squared plus 4x plus 4. Again, we could go through and factor this similar to a simple trinomial. Product and sum, two numbers that multiply to 4 but add and also add to 4. So in this case, these two numbers are 2 and 2. And then we can have it as x plus 2 times x plus 2. Factoring it as a simple trinomial. We could also recognize that the last number is a perfect square. The first number, or the first term, is a perfect square. And when I multiply them together, 2 times x, and then when we double it, we get our middle number. So it does check off all the boxes of being a perfect square trinomial as well. So different ways that we could factor this. The next one, 3x squared minus 5x plus 7. So again, complex trinomial. So we're looking for two numbers that multiply to 3 times 7 or 21. And those same numbers have to add to negative 5. If we think of this, can we think of any factors that multiply to, or any numbers that multiply to 21 but add to negative 5? Well, if we kind of go through our kind of our checklist or we look at our multiplication table, we should find there's 1 and 21, which doesn't work. There is 3 and 7, which gets us to 4, but not 5. And there's no other multiples or nice multiples or factors of 21, or two numbers that multiply to 21. So in this case, there is no factored form. So there's no factored form because we can't factor. Which is okay. And we'll talk about why that's okay later on. And lastly, C, again, looking for two numbers that multiply to 6, or the first number times the last number, 2 times 3. This is a complex one. And they add to the middle, or 5. Again, relatively straightforward. 6, maybe not relatively straightforward. I kind of messed it up. It'd be 3 and 2. So here we can go through, split up our middle term into 3x and 2x. So I have 2x squared plus 3x plus 2x plus 3. I can factor an x out from the first one. That leaves me with 2x plus 3. On the other side, 2x plus 3 is what's on the left side or the right side, so that will be my bracket as well. There is that kind of imaginary or invisible 1 in front. And then when I factor the bracket out, I get 2x plus 3 times x plus 1. So again, this is what we've looked at in the previous lesson, so we should be comfortable, or hopefully we're comfortable factoring. You would have seen this in grade 10 as well. So again, this should be relatively familiar, especially because we've done it over the last couple lessons. The next thing we're going to do is we're going to take a look at our different factored forms, and we're going to look and see how many roots or x-intercepts are there of the previous quadratics. So if I look at the first one, right, my answer was x plus 2 squared, or we could say it as x plus 2 times x plus 2. Now we have to think, okay, this is basically my factored form, right? This is my factored form of a quadratic. So what are the x-intercepts, or what are the roots? And if we think back to our factored form unit or lesson in the previous unit, our x-intercepts are going to be what values of x make these brackets 0. Or we could say it's the opposite of the values in here. So we have -2 and -2, or we could just say my x-intercepts are -2. For B, there is no factored form. So if there's no factored form, I don't have an x plus a value times an x and another value. So what are my roots? What are my x-intercepts in this case? Well, since I don't have a factored form, there are no roots. There are no roots or x-intercepts. So that is saying that this quadratic does not touch our x-axis. And in the last one, x plus 1 times 2x plus 3, right? This is our factored form. Again, a little bit different, but this is kind of the example where we said we have to set each bracket equal to 0. So x plus 1 equals 0. Solve for x. We get x is equal to -1. That one is relatively straightforward. The second one is a little bit harder. 2x plus 3 equals 0. Move the 3 over. I get 2x equals -3. Divide by 2, I get x is equal to -3 over 2. So those are my two x-intercepts for this quadratic, or this parabola, or this expression. So we're seeing three different examples. Right? We're looking at the first one we had 1 x-intercept, the second one we had 0 x-intercepts, and the third one we had 2. So from our factored form, or from factoring an equation in standard form, or a simple trinomial, or a complex trinomial, we can find how many x-intercepts there are by factoring it or turning it into factored form. So a quadratic can have none, or we could say 0, 1, or 2 roots. And when we talk about roots, we're referring to our zeros. I'm just gonna write that here because it's a smaller space. Our zeros or the x-intercepts. So again, this idea is just how we can go from standard form to factored form by factoring. And when we go from standard form to factored form, we can find our x-intercepts. And you can imagine what we're going to do next based on what we've done with the factored form equation in previous lessons. So just in the first one, or in our graphs, we're just going to kind of show examples of how we can have 0 x-intercepts or no x-intercepts. Just in general, what our parabola might look like. So we might have something that looks like this, where the vertex is above the x-axis and it's not touching it at all. It means there's 0 x-intercepts. We could have something where it's the same thing and it's opening down and the vertex is below the x-axis, right? So if it's below the x-axis and opening down, there are no x-intercepts. It's never going to touch the x-axis. For 1 x-intercept or 1 root, just use the different forms. 1 root could look something. I'll use the example from the previous page. We had the x-intercepts of being both, I think it was -2. So we would have a quadratic that might look something like that, where the vertex is on the x-axis. It could be also similar where it opens down, something like this, where again the vertex is on the x-axis. And finally, the other scenario where we have 2 zeros, again, zeros, root, x-intercept, all interchangeable. We would have something where maybe the vertex is above our x-axis and it opens down into it. So it crosses twice. And actually, I'll go back and put them in red, our x-intercept. So it crosses twice. Or we could think vertex is below and it opens up. So again, it still touches twice. So those are just visually the different scenarios that we could have with a parabola and with our x-intercepts. So we could have 0 x-intercepts, we could have 1 x-intercept, or we could have 2 x-intercepts. Again, these are just the different scenarios visually so we can see or have an idea of what they look like or would look like. So what we're going to do in the one example is we're just going to go through and factor our quadratics and determine how many roots there are. Right, so if I go through and determine the number of roots, I need to factor it first. So in this example, we're trying to find two numbers that multiply to 12 but add to -8. In this case, it would be -6, right? -6 and -2. Because it's a simple trinomial, I can just rewrite this as x minus 6 and x minus 2. So from looking from this, how many x-intercepts do I have? Well, I don't even need to go through and calculate if I'm just looking for the number of them. But because I have two different brackets, this should imply that there are two roots. They would actually be the two roots, and they would be 6 and 2. Right? The opposite of what we see in those brackets. The next one, I want to go through and factor this one. I could look at it and say, okay, it's a complex trinomial, so two numbers that multiply to 36, but they add to 12. Okay, in this case, it's 6 and 6. So I'm going to split up that middle term into those two values, 6x plus 6x. We still have the 4x squared and the plus 9 at the end. Factor the first two terms, get common factor of 2x out. That leaves me with 2x plus 3. And the second one, I can factor a positive 3 out, which leaves me with 2x plus 3. I have a common bracket of 2x plus 3 that I can take out, and then it leaves me with 2x plus 3 as the remainder. So this actually works out to a perfect square trinomial because it's just 2x plus 3 squared. Now, again, you could have recognized that it was a perfect square trinomial in the first place and gone through and said, okay, well, let me check. The square root of 9 is 3. The square root of 4x squared is 2x. And if I do the test of the middle number, 3 times 2x times 2 does equal 12x. So if we do that test and we recognize that this is a perfect square trinomial, then I can just take the first term, which is 2x, or the square root of the first term, which is 2x, the square root of the last term, which is 3, take the sign in the middle, or the sign of the b value to be the sign of my bracket, and then it's squared. So either way you choose to do it is fine. Obviously, you can just see one is less work than the other. And once we have, again, it's factored, we can see that there's only one bracket, right? Essentially, there's only one bracket. There's only one root here because the brackets are the same, right? So there's only one root. If I was to go through and solve, right, just off to the side, 2x plus 3 equals 0. Move the 3 over. 2x equals -3. X equals -3 over 2. Right? So again, I have one root because if I was to do the same step with the other bracket, because it's the exact same bracket, I'm going to get the exact same answer. So the other bracket would be -3 over 2 for my one root. Last example, 2x squared plus 12x. So this is a little bit different of a quadratic. It's not a trinomial, right? So it's not a simple trinomial or a complex trinomial. There are two terms. So your first thought might be, okay, it's a difference of squares. However, neither of these numbers are a perfect square. And again, hopefully you have your multiplication table to double check that. Neither of these numbers are perfect squares, and there is no subtraction in the middle. So what can we do? We can't factor it like a trinomial, but what we can do is let's just try to see if we can common factor it. So is there a common factor between 2x squared and 12x? Well, looking at the numbers, I can take, or the coefficients, I can take a factor of 2 out of both. And then looking at the variable, they both have an x, and the lowest degree or the lowest exponent is 1. So I can take a 2x out of both. That leaves me with x plus 6 for my factored form. So in some cases, you might just have to common factor. You might not be able to factor it as a trinomial or a perfect square trinomial or a difference of squares. Now that I have my factored form, I have to think of how many roots are there. Well, we can think, how many factors are there? How many different factors are there? In this case, there's 2. There's the 2x, and there's the x plus 6. So there are 2 roots here. And we might think, okay, well, how do I get 2 roots here? Right, well, we can set both of these equal to 0. 2x is equal to 0. Divide both sides by 2. X is equal to 0. X plus 6. I could just look at that and get my answer, or I could say, okay, x plus 6 equals 0. Move the 6 over. X equals negative 6. So my 2 roots are 0 and negative 6. So again, similar things that we've done before, putting it into factored form and determining how many x-intercepts there are from the factored form. Factored form, again, we should be familiar with, we should be used to. It is something that we've done before and you've done in previous years. The main thing now is just understanding that when we're factoring a trinomial or when we're factoring a quadratic, we are turning it into the factored form and then using that to determine the number of roots, or if we want to, the specific number or the specific roots. So it's all about just kind of showing a connection between the different forms of a quadratic.